Hi, in this video I'm going to describe connecting some vacuum fluorescent display modules to my RC2014 Retrocomputer. If you're unfamiliar with the RC2014, then I recommend you visit the first in my series of RC2014 Z80 Retrocomputing videos, as that video explains a bit about the platform and has the information on where I ordered my original kit from. So anyway, these two things here are vacuum fluorescent display modules. They're kind of like an LCD, but a little more retro in design. They use high voltage. There's typically a high voltage driver on board, so I think you would probably see there's like some inductors and stuff on here that's used to drive the high voltage to operate the display. These are Noritake modules that I'm using, and the nice thing about them is they have the same pinout as popular liquid crystal displays. So that things that are designed to operate with a liquid crystal display will often, you can drop one of these VFDs in place. These two modules use an HD 44780 compatible driver chip, which is something that is very well known, and many people have used displays using that driver chip in their projects using a Raspberry Pi or an Arduino or whatnot. I myself have done videos using the smaller module, interfacing it to a Raspberry Pi. I did that in serial mode. For the RC2014, we're going to do it in 8-bit parallel mode just to do something different. So a few things to note about these modules is looking at the back side of them. Typically they will have 14 pins, either a single row header across the top or a double row header across the side. There will be some jumpers on the back. So you can see this one, I have a jumper right there that I solder bridged. This one had a jumper that I was able to stick a pin header in and put a shorting block across. So you might have to jumper them depending on exactly what you want to do. As opposed to an LCD, you don't have to implement a contrast or brightness control for these. There's no backlight. The vacuum fluorescent display itself does emit light, and the brightness is actually software controllable. So if you go and look at the data sheet will tell you almost everything that you need to know about this display. Typically what I find when I Google is a one-page data sheet. If you go onto Noritake's website, then you can find what they call the full data sheet, which is like 50 pages long and includes much more information. Though this here will tell you almost everything you need to know. Get the full data sheet if you wanted to know how to, like program the character generator or something uncommon. So this is, let's talk about the small display since that's the data sheet I have here. The small display JP6 is a jumper that's used to select between serial and parallel mode. It's traditionally open, which will leave the display in parallel mode, which is what we want for this video. If you wanted to interface it to a Raspberry Pi, then you would probably want to jumper JP6 and put it into serial mode. But we'll leave it in parallel mode so we can operate it in 8-bit. The other jumper is this one for the microprocessor selection. So it can operate in two different modes, 6800 mode or 8080 mode. By default, the jumper is not there and it operates in the 6800 mode. Since we're going to be doing a Z80 computer that we're going to be interfacing this to, so we will want to jumper that across so it operates in the 80 mode instead of the 68 mode. And you can see that here on this one. I installed this pin header and jumper. On the bigger one, right there, I installed a solder bridged it across with a chunk of wire. So this configuration that we're going to go through works on displays that have up to about 4 lines by 20 characters wide. If you get into a display that is bigger than that, then they typically need to have 2 driver chips, and they will often not have the jumper block to switch between 68 and 80 mode. So you'll be stuck in 68 mode. I was not able to successfully interface them easily in 68 mode. So I'm sticking with the ones that I can run in 80 mode, and then I will do I'll do a demo of something in 68 mode in a future video. So let's take a look at the schematic. So over here on the left, typical of my RC2014 projects, we have the RC2014 backplane, which is mostly just the Z80 pins brought out to a 40 pin connector. And then this is relatively simple to interface this module. We'll need the standard chip select logic that we typically use, which is 74 HCT138N 3 to 8 decoder. I often use the A5, A6, and A7 lines. Those allow me to put the device under any of 8 different addresses at 20 hex apart, so 0 hex, 20 hex, 40 hex, 60, 80, A0, C0, or E0. We can put this display module at any of those addresses. So that is hooked up to the, in addition to those address pins, is hooked up to the M1 and the I/O request, so that it will only select the chip when I/O request is low and M1 is high. Now, most of the time that's been sufficient for the logic to interface with the chip, but in this case, these LCD modules, they don't have a chip select. What they do is they just have a read pin and a write pin. That's when operating in the mode 80. And so what we'll need to do is we'll need to combine our chip select logic with the read pin using this OR gate. Then we'll generate an I/O read signal. So whenever this signal goes low, it'll tell the VFD module to read. And then we'll do the same with write. So we'll combine the write signal, chip select logic will generate I/O write. Whenever I/O write goes low, it'll tell the VFD module to write. There's a couple of unused gates on that OR gate chip. We'll just terminate those. Over here, we actually see 2 VFD modules, and what I did there is I used 2 different footprints so we could accommodate both the version that has the 14 pins across the top and the version that has the 14 pins in the double row header along the side. The VFD module, in addition to having I/O read and I/O write, it has 8 data lines, a ground and a hot. And there's this one pin here that's, it can either be unused for the VFD, you can make it a reset input, or you can make it, in the case of an LCD, it might be your contrast input. So I took that pin, that was the 3rd pin down, and I ran it over here to a 3-pin header, so you could either jumper to your reset signal, or if you're using this with an LCD module, you could connect a potentiometer and have a contrast signal for the display. So it's really very simple. I mean, the PC board is going to be almost empty. Let's take a look at the PC board. So here is the version that I built for the one that has the 14 pins across the top. You can see this whole section in the middle here is empty. And over here we have the 74 HCT138, the jumper block to select the address. I've jumpered it to address 0, and the 74 HCT32. Here's the spot for the potentiometer and the jumper for that unused pin, in case you were using it with an LCD. Board is almost the same for the other display, except that it has, instead of the header across the top, we've got the header down the side. We've still got the OR gate. We've still got the 74 HCT138. So to plug this in, this one here plugs in nice and simple. So I designed the board so that the mounting holes are all lined up for this 2x16 display, so I can easily put standoffs and screws in there, and I could make this into a very solid assembly. For the larger, the 2x24, it plugs in on the side. Doesn't sit quite flat because it has this large inductor that sticks out the back, and I wasn't planning on that when I designed the board layout, because that inductor runs right into where my 74 HCT 138 and my address jumpers are at. So it kind of sits crooked. You know, I think if I wanted to, I could get like a stacking header and build this off so that this, you know, if we stacked it off about the height of a stacking header, then it would fit in there about right. So I'll probably do that at some point so it's not sitting crooked like that. But that is one thing to keep in mind with this bigger display. It also has this gigantic capacitor over here on the side, in addition to that inductor. The inductor, I did stick a piece of electrical tape across because I wanted to make sure it wouldn't short up against that jumper block. So that is the two modules assembled. Now we're ready to try them out. Okay, so let's try this out. So I have the RC2014 set up. I'm going to plug the VFD module into the front. Should be good and lined up. Let me give the RC2014 some power. So I do have a serial hooked up in the back here via an FTDI cable. Power goes in through the side. Hit the reset, where is it? The reset button. And there we've loaded CPM. The RC2014, we can have it boot directly into BASIC. I've used BASIC directly in a few of my other videos. One of my more recent videos I showed how to install CPM, so I've generally had it configured to use CPM lately, but there is BASIC installed in my CPM installation, so I can just run Microsoft BASIC. And now we're running BASIC, and we can talk to our VFD. You'll see the VFD itself is not lit. That's because we have to give it some commands first. So the first thing we're going to do, so the LCD, its control port is on port 0. Its data port is on port 1. So if we output something to port 0, it'll be a control command. So hex 30 is what we will output to it to tell it to initialize itself and configure itself for 8-bit mode. So the display's initialized, but it's not on yet. The next thing we can do is we can set the brightness. So the brightness, oddly enough, it goes to port 1. And you can only set the brightness immediately after you do that hex 30 function set. So if we set 0 to port 1, that will be brightest. If we would have written a 3 to port 1, that would have been dimmest. So now we've got the brightness set. We can do back to the control port. So function 1 on the control port will be to clear the display. Already cleared, but why not? We'll clear it anyway. And then finally, you know, it might be handy if we could actually see something. So let's turn the display on. And H0F. So when setting the display on/off, there's a total of 4 bits that get set here. The 4th bit is always a 1. That tells it we're doing the command to set the display state. The 3rd bit is display on or off. The 2nd bit is cursor on or off. And the 1st bit is blink on or off. So we're sending all 4 bits are set with a 0F hex. So what we will do is this will turn on the display, turn on the cursor, and make the cursor blink. Okay, so we have our cursor, it's lit up and blinking. Now if we want to write a character, that will go to port 1. 65 should be an A. So there's an A. 66 would be a B. So you can see it will automatically increment the cursor 1 place. So, I don't know, let's do 70. What character is that? That's an F. Okay, I think that's probably as good as this IP camera I'm using is going to focus on there. You can trust me, it looks a lot clearer in person than it does on the screen there. There's a little bit of bleed over. I think that the pixels are just too bright for the camera. So you can see the letters A, B, and F, which is what I wrote out there. So I have written a longer program. Let me cut and paste that. So what this program will do is it will output the string. I think it says hello world to the top line. So there's our hello world. So I have several subroutines here. Go sub 4300. Clear the screen. Now interesting is what happens if we write a string that is too long. This is a long sentence that takes 2 lines. And then we go sub 4500, that will print that string. So, I mean, you can see we got this is a long S, and then it cut it off, and then we got eins on the bottom. And so the reason that it chopped it off there at the side is that the chip logically addresses this as if the lines were 32 characters wide, I believe. So we should have got the first 16 characters. This is a long S, would have been 16 characters, then we probably lost the next 16 characters. Seems about right. And then the next line is down at the 32 character position. So that's one thing to keep in mind when using these displays, is that you can't just keep writing it and expect it to simply wrap. You do need to execute a command to go down to the next line. There is a command that lets you arbitrarily position at any XY location, and I have a subroutine that does that. That's the subroutine at 4400. So let's go sub 4300 and clear the screen again. Then we'll do an X equals 0, Y equals 0, go sub 4400, and let's do a $T equals line 1. Go sub 4500, there's line 1, X equals 0, Y equals 1, and then let's $T line 2, go sub 4500. So there, we've written line 1 and line 2. You can see that it's pretty easy to interface with this display. Let's try out the longer one and see what it looks like. Plug it in. Reset. Let's load up mbasic again. And we'll run my program. We've got our hello world again. So this display is working just like the other one. Just has more characters, it just has more columns. So let's go sub 4300, clear the screen. This is a long sentence. Go sub 4500. See there, we can see it can fit the whole sentence. And then X equals 0, Y equals 1, go sub. Was here. So yeah, again, working just as it should. So I think this makes a nice retro display for the Retrocomputer. At least for these 2x24 ones, you can display quite a bit of data on them. I think it's okay. We've gone to a bunch of effort here to build a display module. It seems a shame not to implement something useful. So I'm going to turn this RC2014 into a VFD clock. So if you watch my previous video, I built a real-time clock module using a BQ4845 chip. If you haven't watched that video, feel free to pause this one and go back and look. But right now, I'm just going to plug this pre-built module in to our backplane in a vacant slot. Then I'm going to power up the RC2014. Hit the reset switch. So I have a clock program written in BASIC. There is a way for me to set the current time. Let me remind myself how I do that. I think what I do is H equals 15, M equals 33, S equals 0. Go sub 3000. That should set the real-time clock. And then we can just type run. Well, that's very hard to read because it's so freaking bright. If I put in some background light. There, that gave us a little better contrast. But if we just turn on the overhead lights. Okay, so there you can see there is running a clock. Thank you for watching my video. Please visit my website at www.smbaker.com for more electronics projects and sandrail stuff. Bye.